Hey guys, welcome to another video where I'm going to talk about one of the most famous paradox, if not the most famous paradox of all times. Year was 1901. A mathematician called Frege went completely mad just after receiving a letter from Russel, the legendary philosopher himself. What was so important in the letter that drove a prominent mathematician and philosopher to insanity? The answer? A simple looking paradox which was enough to ruin Frege's lifelong work that he did to build the foundation of all of mathematics based solely on symbolic logic. Let's find out what that paradox is. That is known as Russell's paradox today. And also, I'll tell you how you are probably also making the same mistake as Frege did. But first, let's talk about some preliminary concepts or prerequisites that you will need to understand what I'm talking about. Okay? Okay, let me clear this thing first. First, let's talk about what is a set. A collection of arbitrary objects, right? Or arbitrary collection of objects. For example, set of all countries, set of fish in a pond, or set of all the hair on a bald man, which is the null set, obviously. Okay, so you got it. Basically, set is a collection, right? Now, what is an element? Element is the objects that a set contain, right? A set forms by containing all its element. Okay. Now, what is contains? It's basically that the property of the set that it has something. Suppose our set is set of all the integers till 5. Okay, so it would be our, this is 1 starting from 1. Okay, 3, 4 and 5. Now A is a set 1, 2, 3, 4, 5. These are the elements that the set A contains. So I think this is enough basics, and if you have understood this much clearly, you'll understand whole of Russell's paradox quite easily. Okay, now let us construct some interesting sets. Suppose, let me change the color. Suppose C is a set. C is the set of all the cats that you know. Okay, let me just list them down. First cat, let me call it meow. Okay, second one, let me call it meow meow. Okay, and third one, I think okay, let me draw 2 ears. Like, okay, so this is another cat, and basically imagine all the cat that you can think of, including probably your cat, your neighbor's cat, and smelly cat as well, right? All the cats. This is C. Now think about it. Does C contain itself? What do I mean by does C contain itself, right? So does C belong to C? No, because C is a set. This is a set, and only cats belong to C. A set does not belong to C. So we'll say that C does not belong to C, and does not belong is written as this. Okay, C does not belong to C. Now let's think about a new set. Okay, let us call it D. Set of everything that is not a cat. Okay, so probably a dog, probably you, probably the planet Pluto, probably Mumbai locals. How about that? Probably some chicken, because why not? And things like that. Okay, but will there be any cat? No, because D is the set of everything that is not a cat. Okay, so this is our D. Now think about it. Does D contain itself? Okay, the question is, does D belong to D? Yes, the answer is yes. Why? Take a few seconds to think about it. Okay, as I have given you this hint or the answer. Because D is everything that is not a cat. Now what is our D? This is a set. Is a set a cat? No, it is not a cat. So D contains D as well, right? D contains everything that is not a cat, and D is not a cat, so D contains D as well. So D belongs to D, right? So we have understood that there are sets that contain themselves and there are sets that do not contain themselves. Okay, and now let us construct a very cool set. Okay, let me erase whatever we did till now and let us start a phrase. Yeah, there we go. Now let's collect all the sets like D and call it X, namely X. Okay, all the sets that do not contain themselves, or sets like D. Okay, now the question is, does X contain itself? Okay, now let's think about it. This part is very crucial. Okay, so pay attention now. Suppose this is true. Okay, X belongs to X. Now X contains only element like D, so it means that X contains only sets which do not contain themselves, right? Oh, sorry, I made a mistake here. Okay, so D are the sets which contain themselves, right? So it should be like sets like C. Okay, my bad, let me just correct it. Like the set of all the cats, right? Now does X contain itself? Suppose it does. Okay, so that means it's a set like C. So C is a set which does not contain itself. So X, it implies that X does not belong to X. Did you get the logic? Let me explain it to you one more time. Okay, so X belongs to X. So inside X there is X as well. There can only be set like C, right? Like the set that do not contain themselves. Okay, now if X is inside X, that means that X is also like C, right? That means that X also does not contain itself, and this is what you got here. Okay, now if this is not the case, let's see whether opposite can be true or not. Okay, x does not contain itself. Let's see what it leads to. So it's saying that x does not contain itself. Okay, this thing is saying that x does not contain itself. So that means x is a set like C, because C is a set which does not contain itself, right? We just established. So as x contains all the sets like C and x is a set like C, so it means that x contain x because x is a set like C, right? And even this is a contradiction, right? Because we started with x does not belong to x and we got x belong to x. Now again a problem. Do you see what is happening here? So x cannot contain itself, nor can it not contain itself, which is absurd. So definition of set as arbitrary collection of object break down here. And can you guess now where Frege went wrong? This is the mistake that he made. He thought set to be arbitrary collection of object, and his entire work broke down because of this assumption that Bertrand Russell showed to be false, because his definition does not stand here. In mathematics as we know it, there cannot be any inconsistency. Okay. To resolve this paradox, as a response to this, mathematician developed axiomatic set theory. This was primarily developed by two guys called Zermelo and Frankel, and many others also came up with their own set of axioms which can basically prevent this paradox from taking place. Okay, but don't panic. Even if it's not mathematically rigorous, the set theory that you use every day won't really break down until you come across really weird sets like this, sets that contain itself and things like that. And obviously you will have to go to infinity, right? In finite sets, this kind of problem completely does not occur. It never occurs, I mean. So that's all. I hope you have understood what Russell's paradox is saying. And if you like the video, hit the like button and subscribe, and press the bell button as well in case you want to be notified whenever I upload something to give you your daily dose of mathematics. Thank you.